Traditional cryptography relies on two rigid assumptions: high computational capacity and strict secure key management. In emerging infrastructure-less environments like Internet of Things or device-to-device networks, those assumptions break down. The devices are too small, the networks are too fluid, and managing encryption keys across thousands of decentralized nodes creates severe latency. The alternative lies in the physical medium itself. Physical layer security, or PLS, secures data by exploiting the inherent, unavoidable physical imperfections of wireless transmission, specifically signal fading and thermal noise. By utilizing the physics of the propagation channel, PLS bypasses encryption entirely. Instead of hiding a mathematical key from an adversary, it mathematically destroys the signal over the wiretap channel before an eavesdropper's hardware can even process it. To see how this works in practice, we have to look at a specific physical problem. Imagine two source nodes, source 1 and source 2, that need to exchange confidential messages, but they are separated by a physical barrier or severe shadowing that prevents a direct wireless link. Communication is impossible unless we introduce an intermediate relay node to bridge the physical gap between the two sources. This introduces a paradox. In large-scale, heterogeneous networks, the only available relay might be a node with low security clearance. We must rely on this exact hardware to pass confidential messages, even though the relay itself is a potential passive eavesdropper. It is an untrusted relay. A recent paper published in the IEEE Transactions on Vehicular Technology proposes a novel architectural solution to this exact problem: a self-reliant cooperative network that pairs a wireless-powered untrusted relay with a secondary, external node known as a friendly jammer. By introducing a coordinated secondary noise source alongside the primary data transmission, the system overwhelms the relay's decoding capabilities. The untrusted relay is forced to act strictly as a blind courier, securing the end-to-end network without ever having to trust the intermediate hardware. This diagram maps the spatial arrangement of our four half-duplex nodes: the two sources, the untrusted relay, and the friendly jammer, alongside their specific channel coefficients. There is a severe physical constraint built into this architecture. The two helper nodes are completely energy-starved. Possessing no internal batteries, these intermediate nodes rely entirely on wireless energy harvesting to function. They must draw all the power required for their circuitry directly from ambient radio frequency signals. This creates an immediate hardware conflict. A single antenna cannot simultaneously harvest power from an incoming RF wave and process the information embedded within it. This timeline breaks down the proposed time-switching architecture designed to solve the antenna conflict. It divides the total transmission block, designated as T, into three distinct chronological phases. Phase 1 is strictly for energy harvesting. For the duration of alpha T, the two sources broadcast high-power, non-information RF signals. The relay and the jammer act as passive sponges, absorbing this energy to charge their internal capacitors. This specific design choice transforms a standard communications protocol into a strict energy time optimization problem. Without Phase 1, the network has no power and cannot function. But if alpha is set too high, the system wastes the block duration on charging, leaving almost no time for the actual data transmission. Once the nodes are charged, Phase 2, information transmission, begins. Both sources transmit their confidential data into the air simultaneously, creating a superimposed signal at the relay. At that exact microsecond, the friendly jammer uses its newly harvested energy to blast a targeted jamming signal directly at the relay. This specific timing is designed to counter multi-user decoding. In a worst-case eavesdropping scenario, a sophisticated relay will attempt to isolate and decode all incoming source signals simultaneously. The jamming signal floods the relay's receiver, intentionally degrading its signal-to-noise ratio to prevent that extraction. In Phase 3, data broadcasting, the relay takes whatever messy, tangled mix of source data and jamming noise it received, amplifies it, and broadcasts it back out to the two sources. The effectiveness of friendly jamming relies on the sources possessing the exact jamming sequence before the relay broadcasts the data. This is achieved by pre-storing random sequences that the jammer indexes with a shared key, or through a preliminary noise phase. This prior knowledge allows the legitimate sources to perform both self-interference translation and jamming cancellation on the received broadcast. The untrusted relay lacks the key to the jammer sequence. It is permanently stuck with a corrupted signal, unable to extract the confidential data. To evaluate how well this architecture performs, researchers rely on a mathematical metric called the ergodic secrecy sum rate, or ESSR. ESSR is calculated by taking the data capacity of the legitimate end-to-end channel and subtracting the capacity of the eavesdropper's wiretap channel. A positive ESSR means secure data is actively flowing. This calculation must also factor in the power outage probability. If the relay or jammer fails to harvest a minimum predefined threshold of power during phase 1, their circuitry fails to activate. When a power outage occurs, the ESSR drops to 0. Using a pre-shared noise sequence, the network engineers a physical disparity. The wiretap channel's capacity is driven towards 0, while legitimate channels remain crystal clear. This graph plots the ergodic secrecy sum rate against the time-switching ratio, labeled as alpha. The massive peak of the green curve demonstrates the clear superiority of the two-way system utilizing friendly jamming. The concave shape maps the physical trade-off we established earlier. On the far left, when harvesting time alpha is too low, the nodes suffer power outages and the network fails. On the far right, approaching 1 provides maximum power, but leaves insufficient time to transmit the data payload. Furthermore, the optimal alpha is highly sensitive to the physical environment. As the physical distance between the nodes expands, path loss increases. The network must dynamically shift the alpha peak to the right, dedicating more time to energy harvesting to compensate for the weaker incoming RF waves. This chart evaluates competing jamming strategies, tracking the secrecy sum rate as the transmit signal-to-noise ratio scales up. Notice the green dotted line representing a network without jamming, and compare it to the theoretical output of Gaussian noise jamming. Relying on completely random artificial noise, the mathematical modeling yields a counterintuitive proof. In this two-way setup, Gaussian noise jamming actually performs worse than having no jammer at all. Pumping raw, uncoordinated noise into a multi-node environment degrades the legitimate end-to-end links faster than it degrades the eavesdropper's link. Without the ability to perfectly cancel the noise at the final destination, the security measure destroys the very communication it was built to protect. The research provides 3 distinct engineering insights. First, untrusted relays can be safely integrated into networks, provided their wiretap channels are intentionally degraded. Second, wireless energy harvesting cannot rely on static parameters. The time-switching ratio must be dynamically optimized in real time based on path loss. Finally, in two-way untrusted networks, shared key-friendly jamming is an absolute prerequisite. Uncoordinated noise is mathematically counterproductive. These parameters define the critical boundaries for designing the self-reliant, infrastructureless environments expected in advanced 5G and future 6G deployments. To review the complete closed-form expressions and the asymptotic high SNR slope proofs, read the full paper in the IEEE Transactions on Vehicular Technology, linked below.